All right, so my presentation for our ISTC class is on trigonometry. The purpose of this is showing students how to connect algebra and geometry to form what is the content of trigonometry. The way I'm going to be doing this is having them mimic some of the ways that famous mathematicians made all these discoveries and applications themselves. So it is very heavily discovery based. The students will be trying to find new information based on their own understanding in collaborative groups using technology. Also, one of the key goals of this is having students learn to teach themselves, and I'll start to describe that a little bit later. I want them to see how trigonometry fits in their current cognitive structure and build off those previous skills. We're going to be exploring trigonometry based around patterns and theorems that they discover. This is all very student-centered. I want them to kind of dictate how we progress in these types of activities. Some of them will be direct instruction, but what I want to do is I want to use discovery to have students make a connection to a material that would normally be very dry. The class description is it's 11th and 12th graders consisting of 57 students. They have very high digital literacy and competency with devices because we are a magnet program. Almost all of my students who are in 11th and 12th grade honors have taken a coding class before. They also enjoy investigating and playing mathematician. I want to give them a chance to see what mathematicians really do and to see what a mathematician's job really is. It's not just solving a bunch of problems, it's discovering things. My big focus was on interpretism, in essence, Bruner's discovery learning. I'm trying to move away from the traditional educational paradigm and have students become part of the learning process. I want them to be in a cooperative position with the teacher, making decisions for themselves, being more metacognitive and deciding, well, how am I going to learn? How do I learn best? And figuring out how to discover things on their own. I want to teach them how to figure out how to teach themselves, because soon as they approach college, there won't be as many people helping them. They're going to have to do it themselves. I'd like to draw quick attention to Bruner's definition of the discovery, which is right here. Discovery isn't finding out something for the first time, according to Bruner. It's discovering it for yourself in your own mind. And that has, as he says, powerful effects on having students put these things together themselves. They get to put it into their brain as their own piece of knowledge. And that's something, one, that they'll retain onto, and two, is something that if they forget, they can reapply it later and rediscover it. Let's jump into our lessons. The first lesson is on the missing sides of right triangles. My goal is to have students recreate the Chinese proof and then apply it. The Chinese proof is based around shifting different areas. So what they'll be doing is they'll be cutting pieces of paper and sliding them around, a very non-traditional proof, and relating it to the algebraic manipulation, which is, the quantity a plus b squared, etc. They'll be doing that side by side so that, again, they can really focus on the connection between these two things. The reason why I have them discover it and give them a, pretty common assessment is because they've seen the Pythagorean theorem before. What this gives them a chance to do is see its full ranging applications because they proved it on their own. They get to see the fundamental origin of it so they can truly understand it. The learning theory here is Bruner's discovery-based learning. You can kind of scroll through here and read why. When they develop their own proof, it gives them some sort of meaning. They take pride in it. They want to share. They have to justify it. And that means they truly understand it. Lesson number 2 is solving trig equations, which is a pretty dry subject matter and relatively difficult subject matter. And though this is a little bit more algebraically focused, the ratios that they use do have a strong foundation in geometry as well. Students will be working in groups, and one person will become a master of each type. The masters will share their work in a jigsaw type format. As kind of described earlier, they'll split into groups and master each section, and then share in our wiki. The assessment is what I call a trigonometric cat box or a maze. As you can see, this kind of fits the Thorndike style. The reason why I chose this type of assessment is these questions take a very long time. So I want to be able to address and eliminate errors before they become a problem. We're going to use that stimuli response technique to help minimize those errors that could be repeated if they don't receive assessment or if they don't receive feedback until the end of the question. I want to be providing feedback all along the way, and they can't move forward unless they master the underlying concepts first. As mentioned earlier, this is a Thorndike strategy because of his cat box type ideas. What I want to do is I want to show them this whole step as one big process, but they need to be able to understand each one each individual piece. These tendencies will help them grow strong connections and like minimizing the errors, because even though there's an annoying consequence because they have to go back and answer the previous questions if they don't do it correctly. So there is that sort of punishment there. And again, that big focus why I chose this one, eliminate the common errors. Lesson 3 is on the law of sines and cosines. And what I used for this one is kind of a graphic organizer type activity. What the students are going to do. We're going to do kind of like a learning walk. They're going to see the different types of proofs and problems involving sines, law of sines and law of cosines. And then we're going to use a graphic organizer to show how law of sines and cosines fits in with their current understanding of solving for triangles. Right now, they can only solve for missing angles in right triangles and missing sides in right triangles using right triangle trigonometry or the Pythagorean theorem. Here, with this learning web, what they'll be able to do is see how the law of sine and cosine fits in all of their understanding of triangles and see, well, when do I need to use law of cosine versus law of sine versus law of cosines versus when do I need to use the Pythagorean theorem, or when can I use all of them? So it's a really cool way of mixing these triangle congruence proofs as well as algebraic proofs and using that logic of geometry, but having the analytics of algebra there as well. The assessment here is kind of fun. It's a treasure map. So what they'll do is they'll answer a few questions. If you look into my paper, you can see what some of these questions are like. And then I'll actually have them walk through and find an X. What they're going to do is they're going to mark an X on the floor of my classroom because the classroom kind of matches a grid. So whoever gets closest will win. The theory I used here is Azubel's advanced organizer. Again, because I want them to record the skills they already know versus the skills that they need to know and see how this new information fits within not just what we've already learned about trigonometry, but how it fits in with their whole realm of mathematics. They know a lot of this stuff already. I just need to get them there. The next lesson for lesson 4 is on the unit circle. What we're going to be doing for the unit circle is we will be discovering all of the different coordinates on the unit circle and see how mathematicians were able to use trigonometry before a calculator or before these tabular books that became very popular. What the students are going to be doing is a paper folding. And the reason why I chose discovery for this is I could just give them the information and they could just write down everything. But what I want them to get at here is I want them to see all these different patterns. You can see the different coloration that I'm using here, or that's used here, to help the students find these different patterns. And because they're discovering it on their own, it's going to have a much stronger connection than otherwise. You can see that the assessment here is pretty cut and dry, matches exactly with the previous. This is a timed one because it is so important that they can find this information quickly. Another reason why I chose discovery for this is if the students forget how to do an assess or forget how to do the unit circle, they can mimic the discovery process again and actually find those values. So they're using those similar triangles that they already know from geometry and the aspects of the distance formula and coordinate type of things, the cross sections that they'll see in an algebraic class as well. I didn't want them to be doing rote memorization. I don't think that's helpful for this. Yes, we will repeat it a whole bunch of times, but if we can do it right the first time and have them make that connection there, it'll be much more efficient. And again, it also shows how it was done before the calculator was invented. Lesson 5, we have trigonometric identities. Now, this one is a very, very dry lesson, and it covers a good bit of information. So what we'll be doing is I'll be using direct instruction, and then we'll complete a human proof activity, which I'll explain shortly. So the reason why I chose direct instruction is because there's so many different types of questions. I want them to have exposure to each one of those types of questions in an effective manner. I cannot allot a ton of time to this material. And if we're doing the discovery activity for each type of equation, then there'll be 8 lessons worth of material, and I don't have the time to do that. And discovery is important, but direct instruction, as Azubel was a proponent of this, because it is effective with its time. The summative assessment is going to be scaffolded problems. So like the first one, they'll be matching. The second one, they'll be filling in half of the examples. The third one, they'll be writing all of one side. Fourth one, they'll be filling out the whole thing. And then the fifth one, they will actually be writing a proof in paragraph form. So they can see it in a number of different representations. I chose Azubel's Meaningful Learning, as I mentioned earlier, because even though there is direct instruction, I get to show how these types of proofs fit into the proofs that they already know and the properties that they already know from geometry and from algebra. In fact, I mentioned here, one of the things we do is we use this graphic organizer to create a proof toolbox so the kids can write down all the theorems that they think will be helpful from algebra, geometry, algebra 2, and see how it'll be helpful for Trig, and how some of the properties we learn inside of Trig match what they already know, match their cognitive structure. And by having them understand how these proofs fit in with what they already know as proofs, it'll end up saving them a lot of time, so I don't have to reteach the whole proof structure. They already know about mathematical proofs. I just want to build upon that. Lesson 6 is on parametric equations, and you'll notice that the next couple types of lessons are all very similar. They're all graphing based, because that link between graphs and the analytic variables are a huge, huge aspect of parametric equations, or for trigonometry. For this one, what students will do is we'll be using a discovery-based activity on Desmos. So you can see here, Desmos, this, if you're on the website, is a slider. So in real time, it'll actually change the graph, and the students can, as opposed to graphing it by hand, which could take a minute, 2 minutes, 3 minutes, students here can graph 200 different parabolas or 200 different projectile motion problems in about a minute. So they can hypothesize, test, hypothesize, test, hypothesize, test in real time and receive feedback on that. So what they're going to do is they're going to explore different types of functions, create a poster, and share the findings with the class. The assessment, what they're going to do is they're going to be sharing a projectile motion using, it's like a physics simulator, and they'll kind of have to match it using Desmos to see, well, what are the key features and how does my data match up with this equation and how strong is that relationship. As you can probably see, this is discovery-based learning. Students will recognize these changes because they're changing it in real time, and it'll stick with them because they're discovering these relationships. Often for this lesson, they'll share something that I may have never thought of. I'm focused on something else so much that they see something new in the problem. The students will be engaged because they're investigating in this activity. They get to take ownership. They get to say, hey, this is my idea. This is my theorem. Let me justify it. You know, they get to say, this is why my idea of the graphs match my idea of the analytics behind it. And, you know, that type of ownership really pushes them. 7 is on polar equations. Very, very similar activity, but instead of using Desmos, we're using the CAS calculators. So what they're going to be doing is they'll be adjusting the parameters here, checking them in real time and seeing how it changes things like lemicons, rose curves, cardioids, and then recording that information and be able to share that with the class. This is all done on a lab in the calculator. Here's a screenshot below. The assessment is an argumentative piece. So the students will be writing, well, how does polar equations, how are they effective? Why are they different? Why are they still taught? Etc. This is, again, Bruner's discovery-based learning, because I could just give the students a pack of information and say, okay, this is how you do these types of problems. But what I want them to do is I want them to figure it out on their own so it sticks. They're responsible for looking at these patterns that they call it their own. Lesson 8 is on the transformation of functions. Again, very similar to the previous 2 lessons. Here in Desmos, there's 6 or 7 different sliders, so they can see how all of these different variables adjust the graph in real time and figure out, well, how can I make these connections myself to the transformation of functions. The assessment is kind of like a lockbox assessment, so they'll answer a few questions. They'll get a passcode to actually open a physical lock. They love this one. Again, this is Bruner's because they're discovering how they're learning. They're looking for patterns for inquiry-based learning. They're trying it on their own and organizing the information in a way that's most meaningful to them. Lesson 9 is on conic sections. This one is a little bit more of a graphic organizer-based one. What they're going to be doing is using a pre-assessment to kind of see how they fit into their current structure. The assessment is a group of envelopes. It's like the Amazing Race, so they'll keep moving forward with more and more difficult questions. I chose Azubel's meaningful learning theory because conic sections fit inside of graphs that they already know. And they're just going to be manipulating previous information and building new blocks on that material. They'll be able to see how this fits explicitly into mathematics as a whole. The last one is sinusoidal regression, which I'll have to go through quickly. Sinusoidal regression, what they'll do is they'll be using a problem. Again, this is based around information that they're looking at. And what they're going to be doing is using Azubel's advanced organizer. So they'll be able to see how this data matches up using the calculator and see how it all fits into their current understanding of, math in and of itself and these variety of problems. Lastly are my references. If you need to take more time, please go through and listen to it. Thank you very much.